Well, it's time for Wise Guys Wednesday.
That's right. Physics professor at U of I, Nadia Mason, joins us now. Good morning.
Good morning.
Good morning, Nadia. How you doing, wise gal?
Wise gal.
That's what I like, the wise women.
Oh, yes.
All of us. So I have been thinking about the concept of temperature.
Okay.
Because in my research lab, we study what we call low temperature physics.
Okay.
And we do this so we can get to quantum mechanical effects, which I can talk about another time.
Okay.
But basically, to see these, we have to get to a few thousandths of a degree above absolute zero of temperature.
Okay.
And
so as
Emily
close as
hates
you
the
can
cold.
get.
Yeah,
I hate
As
cold.
close as right.
Maybe
And this is as cold as you can get. And so we're not, right. And so usually we think of all things as relative in this world, but it's
Yeah,
unusual to have something we call an absolute zero. And so I
Yeah.
thought I'd talk about what we mean by absolute zero
Sure.
of temperature.
Because I'm sure when you say absolute zero, a lot of people are thinking, okay, 0 degrees.
Close.
But,
Yeah,
you know, relative.
That's
It's not
right.
quite.
That's right. That's not what I mean. So,
Yeah.
but first let's talk about how we measure temperature, right? So
Sure.
usually we
Right.
use a thermometer.
That's
right?
the
There's a
biggest one I've
It is
seen.
me too. That's why I brought it. We're not
Is that
gonna
what you use for the kids? Like, are you sick?
There,
They
measure your
can read it
temperature.
loud and clear.
Never get sick again, or else do I use
never.
this.
Okay, cool.
No, in fact, we're not even going to use it today. It's just for show. We're going to
Okay.
use a digital thermometer.
Got it.
Okay.
'Cause that's so much easier, right? So here's our digital thermometer. I don't know if you can see the scale on the camera, you guys.
Oh, there you go. We can see it.
But you can see, so here I have, cold water here, and that's close to, come on, cold water, it's close to 32 Fahrenheit. And then I have hot water over here, and that should be close to 212 Fahrenheit.
Oh,
Right?
nice.
So, so water boils at 212 and
Yeah.
it freezes at 32.
Right.
But this is the Fahrenheit scale. We use it in this country, but it turns out it's not extremely useful.
Interesting.
In terms of physics, and just in terms of calibration, because the 0 of Fahrenheit is based on the temperature of an equal mixture of salt, water, and ice.
Okay.
And this was just decided by Fahrenheit in the 1700s, and we still use it today. And that's where the
well.
0 of Fahrenheit is.
Interesting.
I mean, some things don't change.
Some things don't change. So the more useful is a Celsius scale. I can switch this here to Celsius, and that's based on water, and we live in a water-based world.
Right.
Got
And
it.
so Celsius is useful because the 0 of Celsius is the freezing point of water. This is close to 0.
Which makes sense.
Yeah, and the boiling of water is defined
back.
as 100 Celsius.
Okay.
Right, and so that's a useful scale for us in terms of how we live. And so we can see. I don't know if you can see this. These are our temperature scales. Can we zoom in on that at all? Okay. So there we go. Okay. So you can see that we have the Celsius, the Fahrenheit scale, and then there's something in the middle called the Kelvin scale, and that's useful. These all convert to each other, but the Kelvin scale has something defined at absolute 0. Okay. And I've also noted the temperature of space because everyone cares about that. That's around 3 degrees Kelvin. It's 3 degrees above absolute 0. So it's very close to 0, but not quite
yet.
there.
Okay.
Right. And so that's minus 273 Celsius, minus 460 Fahrenheit. And so what do we mean by absolute 0 then, if it's not 0 of Celsius or Fahrenheit?
What do we mean now?
I'm going to answer that. So in physics, what we think about in terms of temperature is actually energy.
Okay.
And so when we think of 0 temperature, we think that we understand it as molecules having no motion, no vibrations, no velocity. The molecules are stationary almost, right? So here's a model of that.
You know, that makes so much sense, especially since you're saying space is 3 degrees Kelvin, and how every time we watch movies involving
I'm just
space,
thinking about
nothing's
movies,
moving.
really.
Yeah,
So
it's like a vacuum. And so in a vacuum, basically there's nothing,
Super
things stop
interesting.
colliding with each other and they slow down a lot. And so here you can see
Cool.
in this little model of molecules moving, this would be like, again, overhead on this. This is my, you can see it, but this is my high energy molecules bouncing around. These are high temperature. And then I can lower the temperature, and now they're bouncing slower. It's this lower temperature,
There's the
lower
overhead.
temperature, and even in solids, these things, molecules are vibrating. Atoms are vibrating in solids.
Yep.
And so a low temperature solid has things that are not vibrating, and basically this is our 0 of temperature.
This is a very
Right?
cool gadget.
When things stop moving.
Ah, okay.
And the last thing you can see it in is even this water. If I take hot and cold water and I put a little drop of dye in it, which I'm going to do here.
Oh, no.
I know, that's what I was thinking. What's going to happen?
Overhead here. And basically you'll see as I put the drop of dye in the cold water, it goes in, but it doesn't move very much. See how it just sits there?
It's kind of like a tie-dye.
And then I put it in the hot water.
It just falls.
And, well, you should see it in a second. It starts swirling around.
Yeah.
Do you see how it actually looks like
Boy,
it's
that's
swirling
weird.
and moving everywhere in the hot water?
Oh, my
And so that's because the molecules in the hot water are
moving a
moving
lot
so
faster.
much. They're moving very fast, and they're spreading that water all around.
That's
so
cool.
if you look at it, you actually see things moving in real time. And so that's what happens when things are hot. They move more,
Wow.
and when they're cold, they move less.
This goes way beyond what I learned
in school
about energy and molecules and temperature. This is great. Yeah, I wish I could just do it again and you could be my teacher.
I would love to, and that's why we have this. And the last thing I'll say is there's something even cooler, and I promise we'll try to talk about it next. Cooler. Got it.
Got it. I see what you did there.
And actually, what I mean by cooler is even hotter, because it turns out that there's a whole nother realm of quantum mechanics where things are never quite stationary. They always move a little tiny bit around zero. And so there's never really a zero of motion because of quantum mechanics.
And
so you have to move to the next realm as you start understanding the really minute behavior of atoms.
Well, we're going to move to that realm next week?
Maybe a little later.
We'll find out.
Yeah.
So this was 101. Maybe next it's 102.
Exactly.
Yes, exactly. Nadia, thank you. If you guys have questions for our wise guys or wise women, let us know. Go to our Facebook page. Let us know what you want them to talk about, because they're always looking for ideas, right?
Yep, exactly. Let me know.
Awesome. Well, thanks, Nadia.
So much.
Yeah,
you learn something new every day.
Bringing the temperature down in the studio today. Thank you so much. We'll be right back, you guys, for more of the morning show.